Welcome back to our videos on kinematics. This is the second video on kinematics, and we're going to talk about vorticity. In the first video, the first part, we talked about translational flow. Now we're going to talk about vorticity. And vorticity is simply the spin of a fluid. When we see air spinning, we say that it has some sort of vorticity. These are vortices in the atmosphere. And vorticity can be broken down into two components, either the vorticity as a result of the reference frame. If we're standing out in space looking down on the Earth, we can see that the Earth is spinning, and any place on the Earth would have a spin as a result of the spin of the Earth. But then also there's relative vorticity, which is the vorticity that results from the wind itself. So let's try and get a handle on the vorticity that the air has as a result because of it is in the spinning, it's on the spinning Earth, the atmosphere of the spinning Earth. So because the Earth is spinning, any place on Earth there is some rotation that is apparent from outer space based upon the rotation of the Earth. So we know that in the northern hemisphere, if we look down on the North Pole, the Earth is rotating counterclockwise. Likewise, if we look at the southern pole, the South Pole, we can see that the Earth is actually rotating from that vantage point clockwise. So to get a handle on how fast the Earth is spinning, we know that the Earth rotates once in a day, and one rotation is 360 degrees, or in terms of radians, it would be 2 pi. That's from math. So 2 pi, and the Earth rotates in 24 hours. 2 times pi is 6.28. 24 hours is, of course, 86,400 seconds. So if you divide the radians by the seconds, you get 7.29 times 10 to the minus 5th radians per second. Now that seems kind of esoteric, but that's how many radians in a second, in 1 second. And remember, we're talking MKS units, and as scientists we use radians and we use seconds. If that's a little bit complicated or confusing, you can think of the Earth as rotating 15 degrees for every hour. That's 360 degrees divided by 24. 15 degrees per hour is approximately the width of one time zone. So that gives you some perspective on how fast the Earth is rotating. That's the angular rotation, number of degrees or number of radians per second, per minute, per hour. The Earth is also rotating. If you figure out the distance it travels, you can figure out a tangential velocity of the Earth in meters per second or miles per hour. But it would depend upon what latitude you're at, because the Earth is, of course, wider at the equator, and the axis of rotation is a lot closer to the points on the Earth if you're up in Canada. So it's spinning a lot faster in linear terms. But the angular rotation everywhere on the Earth is the same. So the spin that is apparent on the Earth from outer space depends upon the latitude. And if you are at the equator as the Earth spins, then there's no apparent spin at the horizontal, or not the horizontal, the vertical at the equator. In other words, if you had a flagpole sticking up right at the equator, is that flagpole rotating? Well, it's going around with the Earth, but itself does not rotate with respect to space. So we came up with an equation. This is Coriolis did this back in the 19th century. He said that the Coriolis parameter, in other words, the apparent spin because of the Earth, depends upon latitude. And that latitude, take the sine of the latitude, and that gives you the apparent spin. At the equator, our equator, the latitude is 0, so the sine of 0 is 0. So that gives you no Coriolis spin, no spin. But at the North Pole, of course, we have 90 degrees, and the sine of 90 is 1. So you have 2 times omega, and that would give you of course, omega is our 7.29 times 10 to the minus 5th radians per second. So, depends upon the spin that's apparent at any given location on the Earth, depends upon the latitude, and also depends upon the angular rotation of the Earth. When those are put together, we have the Coriolis parameter, which is a measure of the spin of a point vertical at any given location on the Earth. So as we said, it depends upon the spin of the Earth, and also depends upon your latitude. That's all I have for the Earth's vorticity. In the next video, part 3, we'll talk about relative vorticity, which is a result of the wind.